Good afternoon, everyone, and thanks for coming in on this webinar. Before I begin with this topic of the webinar, linear algebra and its importance in engineering, technology, and culture. So I'll introduce myself a little bit. So I'm Puneet, and I'm currently a researcher in artificial intelligence and human-computer interaction, and that's what the world is going gaga about right now. But much before that, I was a mechanical engineer, so that some of you could relate with me if you're engineers. And then I also shifted to do some research in linear algebra. And so this talk will be all about my experience, like connecting technology, linear algebra, artificial intelligence, and engineering, everything together, and how they are related to each other. So I'll begin with the presentation. So even before going to linear algebra, I want you to be introduced to a book by Edwin Abbott that is called Flatland. It's a romance of many dimensions. It's a book that came out in the 1800s. It's a novel, but there are no humans in the novels, but rather there are mathematical figures that are represented in the novel. So there are lines, there are triangles, there are polygons, circles, everything. But the only thing with these kind of figures in these novels is that they live on a flat land. Flatland meaning a plane. So as you can see here, there is a flatland, a kind of plane in which a square and a line are talking to each other. They can't comprehend anything beyond this flatland. That means they can only interpret the length and the breadth of the plane. They have never seen a third dimension called height. So they're totally unaware of it. And it will be interesting to mention that Edwin also gives a political satire here, because that time women were not represented properly, and that's why he shows a line to represent a wife who has no eyes and no mouth. Square has a mouth and eyes, and he can only talk to the wife. So you can interpret all these figures in a two-dimensional plane, and it can be similar to an ant just walking on a tabletop. So you can imagine that all these figures are on a tabletop, can talk to each other, but can never comprehend anything beyond the 2D, the 3D space we are currently in. So at some point of time in the novel, what happens is that a square is just moving in a flat land, like enjoying its time, and suddenly a sphere which exists in the 3D comes to the flatland to visit this square. So what happens is that the sphere comes in and then passes through the flatland, but the square could not comprehend anything beyond the 2D. It cannot comprehend the height of the thing. So if you see on the right hand side, what actually appears to the square is a point when the sphere touches the flatland, and then when it goes through the flatland, the dot changes into a circle and the radius increases, because it can only see the projection of the sphere right on the flatland. And then when the sphere is exactly in the middle, like the plane is bisecting the sphere, the sphere appears as a huge circle to the square, and then eventually the sphere vanishes, it passes through the flatland, goes away, and then again the square would only see a point. And that's why you see that Edwin has very cleverly mentioned the expressions of the square: normal, anxiety, 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 and couldn't understand anything. And that's what happens. A sphere visits the flatland, and then the squares could only interpret the sphere as a circle and of a particular radius. And sometimes they would say that it's a point circle, and sometimes they would say that's a demon growing in size. They couldn't understand it. So I'll say that the square couldn't understand the sphere as it is. The meaning that the way we interpret the sphere as earth or a ball or a cricket ball or something. The square couldn't interpret it. But why am I talking about all these novels when this entire PPT is on linear algebra? The reason is that I want to talk about the complexity of the world with respect to the square. The complexity of the world was much greater than what the square could interpret. The world was in 3D for the square in the Edwin novel. So what I want to claim here is that our world is much more than the 3D that we perceive. The world that we live in is very complex right now. Kind of complexity I can describe right now, like the way we are talking right now, like we have all gathered together on the Zoom, and then there are multiple routers. Like Many of you, like every one of you, are on their own Wi-Fi routers, and these networks are talking to each other, and everyone is on their laptops, multiple hardware, CD-ROMs are moving. Like, world is way too complex for us to even comprehend. So I am just claiming that the squares in the Edwin novel are us, and the sphere in the novel is the world. But so in order to interpret or understand this complex world right now, we have to go beyond the 3 dimensions. And this is, I'm just claiming this, like, you have to trust me on this. And so I'm just claiming that the world exists beyond 3 dimensions. And when I say beyond 3 dimensions, I'm not saying that it's like some 4D or 5D space. I'm saying that it exists beyond 3 dimensions, and the fourth, fifth dimension can be anything. It can be time or culture or something. But again, the point comes, why linear algebra and these 3 dimensions? The reason is that just trust me for some time. I'll relate everything together. So if we have to go beyond the 3 dimensions, first of all, we have to see the world in terms of numbers, and we have to see everything around us in terms of numbers, because numbers are very much related to mathematics. Mathematics has given this power of numbers to us, and if we continue to see the world in terms of numbers, then we could use mathematics to interpret the world around us. And not only we want to see the world in terms of numbers, but also represent in the numbers in some. What I'm claiming right now, that the world exists in a very complex way, and we have to see the world in terms of numbers, and then represent these numbers in terms of an organized structures, maybe matrices. And the matrices I'm talking about is like nothing. It has to do with the matrix series. Like this is just joke. I'm talking about these scalars, vector, matrix, tensors that you probably have seen in academia if you're in engineering or whatever you're doing right now. You might have studied somewhere, because our school curriculums always follow this. Not to worry about why these numbers are like fixed in a bracket or something. I'm just saying, if you trust me and if you represent the numbers in these forms, we'll be able to understand the complex world around us. So a number can be represented just as a number, and what you call as a vector is just 2 numbers enclosed with brackets, and then there is a matrix in which you can again enclose some numbers. And what I'm saying is that when the numbers are represented in terms of data structures, like this term might be very, very much related to computer scientists, but for other electrical or mechanical engineers, you can interpret that you structure the numbers together in terms of vectors, matrices, or tensors, and they will help us go beyond the 3D space. And the reason why I'm so much on this point, that we have to go beyond the 3 dimension, because it becomes a necessity when one wants to understand the complexity of the world, and we have to use mathematics to go beyond it. But I definitely have to give you some examples in the vicinity, and for you to understand what I even mean that the world is complex. So what I'm saying here, that once you see the world in terms of numbers, and then you can use these numbers and do algebra on them, and that will be the linear algebra. And linear algebra will help you represent numbers, and it will kind of manipulate those numbers to do a lot of things. For example, the graphics that you see on your FIFA games right now, like they have improved so far over the 1 decade, and everything, the computer graphics, everything boils down to linear algebra. If you are like in a network of this WhatsApp university, everyone is sharing so much photos and everything, like you're clicking HD photos and you're sending it to your friends, and then your friend is sending it to you. But definitely the WhatsApp on the databases, they are not storing these photos in the same size, otherwise they have to build huge data centers. So they are kind of compressing it, and again the compressing of a file or an image also boils down to some matrix vector products. And if you're getting some recommendations on Spotify or Netflix, then definitely that is also a problem of linear algebra. That comes under something, I use some jargon here, but matrix factorization. And if you're searching on something on Google, then you would be glad to know, if you search today after this talk, that how does Google even give you results very correctly, but that too in milliseconds, is that you'll find that it tries to find the dominant eigenvector of a matrix that comprises of multiple nodes of humans. And and then self-driving cars. So I'm just saying that the world is complex, and this linear algebra would help you to understand this world. So the complexity of the world is beyond 3D, and we can always take the help of abstraction, like matrices and vectors, to represent the complexity in terms of numbers. And I'm just claiming that linear algebra will help us to manipulate these numbers and will retrieve useful information. I'll even show you an example. It's not that I'm just throwing out to you. I'll show you an example, like how can we even understand the complexity. So when I say that linear algebra will take these numbers and manipulate them and will help you, I'm talking in terms of these mathematical jargons like matrix decomposition, matrix vector products, or you might have to solve a system of linear equations, and then you'll be able to comprehend. So right now, if you're seeing the screen, you will see some, again, some, I'll say these are mathematical jargons, but mathematicians would agree with me, but these are jargons like matrices, eigenvalues, and you might have, like if you have done mathematics 1 and mathematics 2 in your engineering, and I know how, how distant it is from engineering and what you see the real world. Like, even if you study inverse of a matrix, adjoint, eigenvalues, you have heard of all these terms, but I don't know whether you could relate it to the real world or not. And that's why I want to take a particular term, that is the rank of a matrix. I don't know whether you've heard of it, but it's a property of a matrix, and show you how it can be, how is it is actually being used in the world right now. So let's say, like, I'll just do a case study and tell you. So on the right hand side, you can see a beautiful Trump, and it's like standing in front of the White House. And this particular image is like 3.3 megabytes. I downloaded it from the internet. It's HD image. So what I want to do is that I want to compress this image. I want to reduce the size of this image, and also make sure that any person with common human vision could interpret Trump, and the size of the image also reduces. So I'll tell you how all these software companies and people use linear algebra to do this. So what they do is that they take this image, and they first of all calculate the pixels. Like, I don't know whether I can annotate here, or I don't think I can annotate, but okay, I'll just tell you that what they do is that they convert the entire image in terms of multiple squares. Like, they will divide the image into many rows, and these will be 4032 rows and 5040 columns. And the squares, they will divide the image into multiple squares, and so ultimately this entire image gets transformed into a matrix. And they will put, obviously, if you convert if you're representing a matrix, you have to put some numbers in the matrix. So the numbers that they put is like, they'll put 0 for black and 255 for white, and anything in between white and black, they will put a number between 0 to 255. I'll explain in the next PPT what I'm even meaning when I say putting numbers in an image. But I want to tell you that we use rank as a property of a matrix to compress this image. So our goal is to compress this image and to reduce it from 3.3 megabytes to something in kilobytes. And this is what will happen. We take a shape of a Donald Trump, like, sorry, the image of a Donald Trump, and then we represent it in terms of matrix. What I mean by matrix is that I divide this image into multiple rows and multiple columns, and then write in terms of numbers. So the reason you are seeing 0 here at the end, because the small square here is totally black, and that's why I'm seeing 0. So 0 represents extreme black, and 255 represents extreme white, and that is the reason that you're seeing 171 around here, because it's kind of very close to white, grayish. So it's still a Donald Trump, but I'm just representing the entire image in terms of a matrix. Okay, so the current rank of the matrix is 4032. So you have to, like, agree with me in why I'm saying, like, I have calculated this rank of a matrix. It's a property of a matrix, and it's like 4032. And you can go either way. You can take this image of a Donald Trump, represent it in terms of a matrix, or you can convert this matrix and again use these numbers to represent this image. You can go either way. So what I'll do is I'll take this matrix and use some algorithms of linear algebra, and this is what you study like determinants, everything, and I'll use all these complexity matrix vector products, and I'll reduce the rank of the matrix. So I'm not even concerned about the image in a way. I'm just taking the image and converting it into a matrix, and then reducing the rank of the matrix. So so there are algorithms to reduce the rank of a matrix, and you reduce the rank of the matrix to 1000. So the previous rank of the matrix was 4032, and we have converted this rank of the matrix to 1000. And in a way, the matrix has also changed. It has changed its numbers. So what I'll do is that after I have reduced the rank of the matrix, I'll again convert this matrix into an image, and let's see if the trump appears again or not. So if you see on the left hand side here, you'll see that what I have done is I have converted this image of 4032 rank into 3 images of 3 different ranks: rank 10, rank 1000, and rank 3000. So if you see on the extreme right, if I desperately try to reduce the rank of a matrix, then the trump kind of blurries away, and still many of us would say that I can easily see that there is a trump over here, but it's kind of in a very blurred way. So if you kind of reduce the rank in a very minimal scale like 4032 to 3000, it's still Donald Trump. What's the fun here is that you convert the Donald Trump even to a rank of 1000, and I'm not saying even 10, only 1000, and then the size of the image has been reduced to 115 kilobytes. Just imagine, from 3.3 megabytes to 115 kilobytes. And you would say, why would I even want to do this? Like, I don't want, like, I can store 3.3 megabytes on my phone. Why would I need 115 kilobytes? But you have to imagine the scale of a company like Instagram. A company like Instagram, in which billions of people are storing billions of images every day, like posting, sharing stories and everything. And there are like the resolution of those images are huge. So when you're working on that scale, like your world is an oyster, and you're taking images from everyone in the world, and they're making their account, then you have to consider that you can't store those images, 3.3 megabytes images, every time someone uploads it on your databases. You have to make sure that you compress it, and then you can eventually, when the person is looking at the image, you can again turn that image into 3.3 megabytes. So this is just a rough demonstration how the real world uses linear algebra. So yeah. So what I've told you right now is a kind of algorithm known as low rank approximation. You can search for it, like you'll find it. That's how people do it nowadays. So they reduce the rank of, converts the image into a matrix and reduce the rank of the matrix, and then the image kind of blurs out, you can say, and then still it's interpretable. So the answer is that it should be interpretable, and definitely it is interpretable. But this is not, these applications of linear algebra are not restricted to images and all. What you're seeing on the screen right now is a robot. If you're mechanical or electrical engineers, definitely you already know about this. This is a robot called Cheetah by Boston Dynamics, a company that Google bought like 10 years ago. If you're a mechanical or electrical engineer, you probably also understand that the complexity in making such a robot, that many of you, if you have done final year projects, you know how difficult it is to even make a 6-legged robot. And these guys have made like almost a robot like a dog, and they're pushing it, and it's kind of stabilizing itself. And I just want to say that the complexity involved in this, like multiple variables will be involved. There will be stress, strain, torque, temperature, and whether the person is pushing, what force it's pushing, multiple sensors involved, and everything eventually boils down to solving a system of linear equations. When I say system of linear equation, I mean just some equation that you might have solved in high school. 3x plus 2y is equal to 5, 2x plus 3 8 is equal to 3, z is equal to 8. But these will not be in x, y, z. It will be like billions of variables will be involved, and you have to solve it using linear algebra. So I'm just saying that linear algebra is also used in all these robotics and all. And if you're having Netflix and you're getting time to watch series in this pandemic, you'll find that not only Netflix has a lot of movies, but it also tries to give you personalized recommendation. I mean that it tries to learn from your behavior and try to understand that if you're watching romantic movies or you're watching serial killer movies, and they want to recommend the movies according to that fashion. And what's inherently Netflix is doing is kind of doing a matrix factorization. It's taking a matrix and then decomposing it into two matrices and then solving something. So basically they are using linear algebra at the back end. So people would say that their algorithms, they're using machine learning. Everyone wants to talk about machine learning and deep learning right now. So people are using deep learning, but inherently deep learning is also involving matrix vector products. Just a matrix is multiplying with a vector and that's all. But you can see the complexity it is able to solve. And that's why I want to connect, like, the world is very complex and linear algebra is helping us to interpret it. And if you're a mechanical engineer, you might have used CATIA or SolidWorks, and you know that how stress strain you try to figure out whether these things will break or not. And this area also comes under finite element analysis. People try to use this analysis and try to find that whether a particular, like a gear or a brake, will fail or a truss will fail given this kind of force being applied. For example, there's a huge wind coming, whether this bridge will fall or not. And then this also eventually boils down to solving a linear algebra problem such that Ax is equal to B. So everything boils down to solving a system of linear equations and doing some algebra on high dimensional data. And that's why I wanted to say that it's a high dimensional data, but I don't want to say that it's like spatial data. It is in high dimension. Probably if you're not living in under a hood, it's deep learning would be new to you. Anywhere you search that, you'll find that deep learning is there. And it's if you don't know, I'll just say a few words about it. Just a way of mimicking brain. On the right hand side, if you see, I've just shared a GIF of neurons and what is happening inside the brain. These neurons are passing signals to multiple neurons and trying to make a sense of the complex world. And on the left hand side, you can see what computer scientists and mathematicians have worked together and created an abstraction of this brain. They have these circles that you're seeing are kind of neurons, and they're also kind of passing electrical signals to different neurons. And like kind of a dog and a cat image is passed, and on the right hand side the output is showing it's a dog. So it is kind of interpreting this complex world. But if you really talk with researchers in deep learning, they won't say that it's like good algorithm. They would say that it's just a matrix vector product that is happening and complex functions being applied on that. So it's again linear algebra. And then if you want to take it beyond all of this, then you'll see that if you really want to, like already Tesla is making self-driving cars. It is working on a very minuscule scale because there are government regulations and all, but they're using again computer vision technologies. What you're seeing right now is like a kind of a car, not a self-driving, but a car. You can imagine it as a self-driving car. It is driving and it is also kind of doing an object detection. What I mean by object detection, that while it is traveling, there is a camera fitted in the bonnet and it is trying to predict whatever it sees in the close proximity. And there is a probability which says that this is a car which is 69% or something. And all these computer vision algorithms, which will be used in self-driving cars and autonomous vehicles in the future, will be using convolutional neural networks, which are also again in the deep learning frame. But then it also boils down to doing matrix vector products. So if you know like complex linear algebra, like if you know linear algebra in its like very rigorous form, you will be able to understand why these algorithms are working. Like everyone wants to talk about programming, and this is good, but if you know about linear algebra, then you also know the crux of the problem, how and why it's only 75% and why it's less. So yeah, so I was thinking about where linear algebra is used, and there's no better way to find where it is used than Google. And if you search on use of linear algebra in Google, you'll find that every engineering or every domain that is existing right now, you'll find that linear algebra is a part of it. And yeah, so it's funny that people have searched use of linear algebra in real life much more than use of linear algebra in computer science. But that's it. Like linear algebra is being used everywhere. This is probably my last slide, but this is a very uncommon view that I want to talk about. because whatever we have talked about is very glamorous in a way, that linear algebra will be used in artificial intelligence, everything. But it's when you're addressing people in hundreds, it's a good way to share this view also, that what is happening right now, we are living in a world of artificial intelligence and machine learning, and these algorithms are like working on their own, and people are getting afraid whether AI will take over or not, or whether self-driving car is like worth or not. Because if you are purchasing a self-driving car, and you definitely don't want the self-driving car to do an accident and kill you, because you are buying that self-driving car. So, but you see, if like, for example, in July 2015, a Google algorithm mistakenly captioned photos of black people as gorillas. So this algorithm, what they're talking about is again a deep learning algorithm, but inherently it is doing matrix vector products. So it's not that linear algebra is only limited to industry or academia. It's also entering into our culture. Probably you might not relate to this racism kind of thing in India, but if you think about how these elections are going on, and what kind of views you're having about the world right now, what feeds are you seeing on the Facebook, and what kind of images that you're seeing on Instagram or Twitter, what posts are you seeing, are like inherently some algorithm that are learning from your behavior, and then calculating your behavior, and then giving you some, because there are millions of people sharing posts, but eventually you like end up using Instagram for only like probably 1 hour or something for a day, if you're a decent user. And for that 1 hour, Instagram makes sure that you see all those kind of images that it wants you to see, so that you come again to Instagram. And this kind of inherently also creates a perception of the world for you, because if you're seeing like everyone is living a very cool life around you, you'll feel that everyone is like actually very happy. And if you see a lot of posts of people killing each other and everything, and then you see the world in a very different way. So I'm just saying that all these matrices and vectors we're talking about are not limited to mathematics right now. The world has changed, and these algorithms and matrices, vectors, and everything, computer vision, have entangled together. So we are living in a very multi and interdisciplinary kind of world right now. So it's nothing is very apart. So culture, technology, engineering, everything is like entangled together, and they're talking to each other, and they want to talk to each other. And that's why I wanted to put up this slide as well, that LA is also entered the culture. So it's a good time to get a sense of linear algebra. So that's from my side. Thank you.